Hello everybody, welcome to lecture 14. So the theme today is that we can represent basically any linear transformation by means of matrices. And once we have bases in mind for the vector spaces, which are the domain and target of the linear transformation. So the basic setup, just to recall, we have a pair of vector spaces over some field F, so think of them as being real vector spaces of columns, if you like. And we have a linear transformation from V to W. So let's just remember what that means. So to say that this function phi from V to W is a linear transformation means that whenever we apply phi to the sum of two elements in V, we get the same outcome as if we applied phi separately to the two elements, which takes us over to W, and then did the addition over in W. So here our vector spaces are equipped with an addition operation. And that means that whenever we have a function from one to another, we can think about how that function behaves with regard to the addition operation. So basically, something to think about here is if we have a pair of elements of V, U and V, and we have a function that takes V into W, then with our pair of elements, there are different things we can do with them. We can apply the function to them to bring them into W, or since we happen to be in a vector space and we have two elements, we can add them together. So we say that the function respects the addition operation if for all pairs of elements of the domain V, if we add the elements together in V, get a single vector in V and apply phi to that takes us into W. If we always get the same outcome by doing that and by separately mapping the two elements from V into W and then doing the addition over in W, then we say that the function respects addition. So we should bear in mind here that in this equation that sort of summarizes that property, that the plus sign in the left-hand side of it refers to the addition of the vector space V, and the plus sign at the right-hand side of it refers to the addition in the vector space W, so they're not necessarily exactly the same thing. So that's one of the requirements that phi must satisfy in order to qualify for the title of linear transformation. The other one is that given, again, a vector in V, an element of V, the other thing we can do besides add it to something is we can multiply it by a scalar. And in order to be called a linear transformation, the function phi must also have the property that for every vector V in V, and every scalar lambda, that the result of applying the function phi to lambda times V, that scalar multiple of V, should give us the same outcome as if we first of all apply phi to V itself, and then do the multiplication by lambda over in W. So again, both sides of this equation refer to kind of slightly different things. The lambda V in the left-hand side here refers to the element V of V multiplied by the scalar lambda within the vector space V, and over here, this image of V, phi of V, that's an element of W. And so the lambda times phi of V here refers to the scalar multiplication in W. So those are the two properties that a function must satisfy in order to be considered to be a linear transformation. And I guess they kind of describe a sort of compatibility of the behavior of the function with the vector space structures on both V and W. And of course, there are plenty of functions between vector spaces that are not linear transformations. And indeed, some of them are of interest in linear algebra. But the functions that are linear transformations are particularly amenable to study via the methods and techniques and principles of linear algebra. So, okay, here's an example. And this example is kind of pulled out of nowhere in a way, but really the theme of this lecture is that this example is actually completely typical of all examples of linear transformations. So let's suppose that we have a matrix with entries in a field F, so real numbers or whatever. We don't necessarily assume that the matrix is square, so it's an m by n matrix. M and n might be different from each other, or they might be the same. Then the assertion is that left multiplication by A defines a linear transformation from the space of column vectors Fn to the space of column vectors Fm. Okay, so let's think about that. A is a m by n matrix. So things that can be multiplied on the left by A are vectors whose number of entries is the same as the number of entries in a row of A, and that's n. So certainly, left multiplication by A applies itself to elements of Fn. And when we multiply an element of Fn, that's a column with n entries, on the left by A, what we're doing is we're taking the linear combination of the n columns of A with the entries of this vector. And the result of that is a column in Fm, because it's a linear combination of columns that have m entries. So for example, this 2 by 3 matrix with real entries defines a linear transformation from R3 to R2. And what that transformation does to a vector ABC is it just takes the linear combination of the columns of A with coefficients ABC, that's the matrix vector product of A with the vector ABC. And of course, the entries of that we can easily write down, and naturally they depend on A, B, and C. And we get 2A plus 3B plus C in the first entry and A minus 2B plus C in the second. And you can check easily using the fact that matrix multiplication and matrix addition have satisfied the usual sort of distributive properties and so on, that this is indeed a linear transformation. Okay, so remark is a couple of remarks. One is that if we think about this, so the approach with this example has been to kind of start with the matrix A and define the linear transformation determined as left multiplication by A. But another way to look at this is if we take the 3 standard basis vectors of R3 and apply this left multiplication to them by this matrix A, well, 1, 0, 0 would go to the linear combination of the 3 columns with coefficients 1, 0, 0, which would be just the first column, 2, 1 of the matrix A. And similarly, the other 2 standard basis vectors of R3, E2 and E3, 0, 1, 0 and 0, 0, 1, their images under this transformation are the second and third columns of A. So essentially, the columns of the matrix, when we think of the matrix as a linear transformation, are the images of the standard basis vectors. Okay, so that's an example of a linear transformation. And there, not surprisingly, since this has been the kind of theme throughout the last few weeks, you'll not be surprised to hear me say that the premise now is that basically every linear transformation looks like that one in the example that we just looked at. So, okay, with some qualifiers, and the main one being that once we choose bases for the domain and target space of our linear transformation, it immediately becomes representable as left multiplication by a matrix. And this is a really useful device because it means if we want to understand linear transformations, what they can do, and how they behave, and how they interact with each other, we can understand all of that at the level of matrices, which in principle is maybe an easier prospect for a couple of reasons. One is that we understand matrix algebra sort of reasonably well. And the other is that vector spaces can really come from anywhere. They don't have to resemble each other at all in terms of what their elements look like, for instance. But we're saying that if we choose a basis for them, then they all look the same. They all just look like the space of column vectors over our field. So somehow, you know, we can develop a theory that applies at once to all vector spaces, regardless of what they actually look like or where they come from or what their elements are. Okay, so now let's give ourselves a little bit of notation and names to things. So let's suppose that n is the dimension of V and that m is the dimension of W. And we're talking about a linear transformation from V to W. So it would, if it were a kind of matrix situation, it would correspond to an n by m matrix. So if we choose bases, and I'll just call them BV and BW for V and W, so BV will have n elements and BW will have m elements, then every linear transformation from V to W, I claim, looks like the one in the last slide is just represented as left multiplication of columns representing elements of V, columns of length n, by some m by n matrix. And of course, what that will spit out will be a vector of length m, a column of length m, which will have the coordinates with respect to our chosen basis of W for the element of W, which is the image of the element of V that we started with. Okay, so I wanted to mention an example that doesn't come from sort of Rn or Rm or some space that already kind of has a coordinate system set up. And also an example that's sort of familiar to us from another area, namely calculus, I guess. So the example is a differential operator, which acts as a linear transformation on the space of all polynomials, we'll say, with real coefficients. So the differential operator, it's referred to as an operator because it sort of takes functions to functions, but it is a function and it is a linear transformation. So if we think about the vector space Rx, consisting of all polynomials with coefficients in the real numbers, so they're sums of powers of x, as constant term, and x to the 1 term, and x squared term, and x cubed term, and so on. Every polynomial has finitely many of those powers appearing with non-zero coefficient. And the differential operator, what it does to any element, any polynomial, is it just sends it to its derivative. And we know that the derivatives have an additive property for functions in general, but in particular for polynomials, that the derivative of the sum of two polynomials is the sum of their derivatives. This is something that we use all the time when we're studying differentiation without probably giving it a whole lot of attention, because it kind of works in the natural way. Like if we want to differentiate x cubed plus 4 plus 2x squared, we can just differentiate through the addition signs because the differential operator respects addition. Also, if we want to differentiate 4 times x cubed, that's the same as differentiating x cubed and multiplying the result by 4. So the differential operator respects multiplication by scalars. Okay, so D, this differential operator, so it takes a polynomial, maps it to its derivative, and it's a linear transformation from Rx to space of all polynomials with coefficients in R. Okay, so the assertion is we can represent this as a matrix. Okay, small problem. Rx is an infinite dimensional vector space over the real numbers R, so we can't really write down a basis of it and write down the coordinates of every polynomial because we have an infinite number of basis elements to worry about. So to make life easy for ourselves, the way we will get around that for the purposes of our example is we won't look at the differential operator as applying to all of real polynomials. We'll just restrict to a finite dimensional subspace. And the subspace that we will choose is P3. So just remember what P3 is. We've used this notation before. Unfortunately, my tablet's not working. I'm sorry, I can't write it on the slides. But P3 is the subspace of Rx consisting of all those polynomials whose degree is at most 3. So polynomials that are at most cubic. So they can look like ax cubed plus bx squared plus cx plus d, but they can't have any terms appearing of degree higher than 3. Okay, so of course, if you differentiate a polynomial, then on each term, the power of x decreases by 1. So if you have a polynomial which is cubic, then its derivative is quadratic. If you have a polynomial whose quadratic, its derivative is linear. If you have a polynomial whose linear, its derivative is constant. So basically, if we apply the differential operator to all polynomials that are at most cubic, their images, after being differentiated, their derivatives are at most quadratic. So we can regard the polynomial, or the differential operator as taking up, as applying itself to elements of P3, which are polynomials that are at most cubic, and as sending them to polynomials that are at most quadratic, so elements of P2. P2 is the space of all polynomials of the form ax squared plus bx plus c for real numbers a, b, and c. Okay, so this is what we're talking about. A function whose domain is a set of all at most cubic polynomials, whose target space is a set of all at most quadratic polynomials, and what it does to what this function does to a polynomial in P3 is take its derivative. And we can verify from the properties of derivatives that this thing is indeed a linear transformation. It respects addition and scalar multiplication of polynomials. Okay, so the assertion is we should be able to interpret this transformation then as a matrix. It's a mapping from a 4-dimensional space. P3 has dimension 4. Okay, its elements have a constant term, an x term, an x squared term, and an x cubed term, which are all independent. So it's a 4-dimensional space. P2, the space of at most quadratic polynomials, has dimension 3. Its elements have a linear term, a constant term, a linear term, and a quadratic term. So x cubed, x squared, x, and 1, which we'll call B3, and x squared, x1, which we'll call B2, are respectively bases for the spaces P3 and P2. Okay, P3 is a space of all linear combinations of these 4 kind of basic elements, and P2 is a space of all linear combinations of these 3. Okay, so to figure out how to describe the differential operator as a matrix, we should expect that it should be a 3x4 matrix because it's acting on a domain that's 4-dimensional, and the images of the elements there live in a 3-dimensional space. So a 3x4 matrix should describe this thing if you believe the statement in the heading of this slide. And to figure out what that matrix should look like, we should look at the images. We've chosen a basis for P3, so we should look at the images of the elements of that basis. Okay, so under the linear transformation D, the image of x cubed is 3x squared. The coordinates of 3x squared with respect to the basis B2 are 3x squared plus 0x plus 0, so 3, 0, 0. So we write those entries as a column vector and just note B2 to indicate that we're talking about coordinates with respect to the basis B2. Okay, that's the first basis element from B3. The second one, x squared, its image under the differential operator is 2x. Coordinates of 2x with respect to B2, it's 0x squared plus 2x plus 0 times 1, so 0, 2, 0 with respect to B2. X is the third basis element in B3. Its image under the differential operator is 1. The derivative of x is 1. Coordinates of 1 with respect to B2 are 0x squared, 0x, 1, 1, so 0, 0, 1. And finally, the fourth basis element of B3 is 1. It's a constant polynomial. Its derivative is 0. So the coordinates of that derivative with respect to B2 are all 0. Okay, so then to figure out the the coordinates with respect to B2 of the derivative of any polynomial in P3 and sort of relate them to these columns, we should give ourselves a polynomial in P3. So here's a typical polynomial in P3. Its coordinates with respect to the basis elements of B3, which are x cubed, x squared, x1, are a, b, c, d. So with respect to B3, it's represented by the column a, b, c, d. Probably I should have a B3 subscript here to indicate that that's the basis we're talking about. And the B2 coordinates of the derivative of P should be given as follows. So P is a times x cubed, the first basis element of B3. So its derivative should be given in the coordinates of B2 by a multiplied by the B2 coordinates of the derivative of x cubed. That's 3x squared. Its coordinates 3x squared, 0x, 1. 0 times 1. Okay. Plus we should have b times the coordinates with respect to the basis B2 of the derivative of x squared. Derivative of x squared is 2x, that's 0x squared plus 2x plus 0, 1. Plus c times derivative of x, coordinates with respect to B2 of the derivative of x are 0, 0, 1, and d times derivative of d, which is 0, derivative of 1, which is 0. So basically, the B2 coordinates of the derivative of this general polynomial P are given by a times the derivative of x cubed, which in B2 coordinates is that column, plus b times derivative of x squared, which in B2 coordinates is this column, and so on. And that, of course, is nothing but a linear combination of these four columns with coefficients a, b, c, d. So yet again, it's a matrix vector product. It's this linear combination of columns. This matrix, this 3x4 matrix, multiplied by the vector a, b, c, d. The result of that operation, of course, is a column vector of length 3. What it is the coordinates of the derivative of this p of x with respect to the basis x squared, x1. So this 3x4 matrix is referred to as the matrix of the differential operator with respect to the bases B3 of the domain P3 and B2 of the target P2. Its columns are the images under D of the elements of B3, excuse me, that should be a B3, written as coordinates with respect to B2. And this one should be a B2, apologies for that. So to apply this operator to any polynomial P of x, we should write P of x as a column vector with respect to P3, and then multiply that column vector by the matrix. And the result of that is a column with 3 entries. It's not written as a polynomial, but we interpret the 3 entries as the coefficients of the polynomial in question. So let's just look at a quick example just to see how that goes. Okay, so here's an example of a polynomial P of x in P3. It's cubic. And to figure out what the derivative of P of x is using this method, which I am not claiming for a second is the sort of recommended method of calculating derivatives of polynomials, it's kind of more to illustrate the point about linear transformations and matrices. We should write the coordinates of P of x with respect to our basis B3, which would be 4 minus 2, 1 minus 3. This is with respect to B3, I guess, if we need to write that. And when we calculate the matrix product, of course, we're taking, you know, it's because of all the zeros in the matrix, whoops, that one's supposed to be a 0. It's a relatively straightforward calculation. In the first entry, we get 3 times 4 plus 0 times everything else, so we get 12. In the second position, we get 2 times minus 2. In the third position, we get 3 times 1. And of course, those three products are exactly what we would be calculating if we just differentiated this polynomial term by term directly. But we should interpret this as being the coordinates of an element of P2 with respect to B2, and the element of P2 that's represented by that set of coordinates is 12x squared minus 4x plus 3, which of course we can easily, oops, I didn't even manage to calculate it correctly. This is a 1, not a 3, apologies. The third entry here is 0 times 4 plus 0 times minus 2 plus 1 times 1 plus 0. So this is 1, and this is plus 1. And now that we've got it right, or that I've got it right, we can observe that that is indeed equal to the derivative p dash of x. If we differentiate p of x, we get 12x squared minus 4x plus 1. So this is not at all sort of intended as kind of advice about how to differentiate polynomials, although if you were trying to automate the process, it might be useful. But basically, it's a device for sort of translating the differentiation of polynomials into a matrix multiplication exercise, which applies to any linear transformation. So there's one more point that I want to make about this while we're on the subject, which is just to make the comment that this matrix works subject to a particular choice of basis that we made for the two spaces, both P3 and P2, and that we do have it open to us to change that choice. And if we were to do that, then we would also change the matrix. So we'll just follow up now with the sort of second version of the same example, but considered with respect to a different basis for P3. Okay, so just to finish up this discussion with a slightly different choice of example, the remark is that the matrix that we wrote down in the last example, which is just written there in the last slide, this 3x4 matrix, depends on the choice of basis that we made for our two original spaces. So suppose we keep the basis B2 of P2, which consisted of the elements x squared, x, and 1, but instead of B3 that we were using, we take an alternative basis of P3. So let's take x cubed plus x squared plus x plus 1, and 1 instead as our basis of P3. And we can sort of satisfy ourselves fairly quickly, I guess, that every polynomial of degree at most 3 is a linear combination of the elements of C3 here. Certainly 1 is there and x plus 1 is there, so x is in the span of these two elements. Once we know that, then x squared is in the span of the last three elements, and once we know that, then x cubed plus x squared is there, so x cubed is also in the linear span. So C3 here is an alternative basis of the space P3. Okay, so if you want to calculate the matrix of the differential operator with respect to this choice of basis for P3, along with the same original choice for P2, then you have to do things just slightly differently. Okay, so what we should have in the columns of our matrix should be the coordinates with respect to B2 of the derivatives of the elements of C3. Okay, so the matrix with the differential operator with respect to this choice should have the B2 coordinates of the derivatives of the elements of C3 as its columns. So if we look at the first element of C3, that's x cubed plus x squared. Its derivative is 3x squared plus 2x. So in terms of the elements of B2, that's 3 times x squared plus 2 times x plus 0 times 1. So the elements of the first column here, the entries in the first column, correspond to the coefficients of x squared, x, and 1 in the derivative of the first element of C3, which is x cubed plus x squared. So we get 3x squared, 2x, 0 times the constant term. For the second column, we should move on to the second element of our basis, C3. That's x squared plus x. Its derivative is 2x plus 1. And with respect to the basis B2, the coordinates of 2x plus 1 are 0, x squared plus 2 times x plus 1. Third basis element is x plus 1. Its derivative is 1. And with respect to B2, the coordinates of 1 are, but it's 0, x squared plus 0, x plus 1, 1. So it's just 0, 0, 1 again. And finally, the fourth basis element in C3 has derivative 0. So that's a column full of zeros in the fourth position. Okay, so this would be the matrix of the differential operator from P3 to P2 with respect to the bases C3 for P3 and B2 for P2. Okay, how does this apply if you want to actually use it to calculate the derivative of some polynomial, which again, I don't really recommend, but if you did, how would you go about it? Well, what this matrix should do, if you want to use it to calculate the derivative of some polynomial, is you should write the polynomial as a column vector in its coordinates with respect to C3, which is the basis with respect to which this matrix is written. So that means we have to figure out, if we give ourselves some polynomial, how to write it in terms of the basis C3. Then we have a column vector with 4 entries, the C3 coordinates of this vector. We can multiply that by the matrix, and the output of that should be the derivative of the polynomial with respect to the basis B2. So our first task here, if we want to apply this to the polynomial fx, is to write the polynomial fx as a linear combination of the elements of C3. Okay, fx has got an x cubed in it. The only basis element in C3 that has an x cubed is x cubed plus x squared. So to have x cubed, we should take x cubed plus x squared. We should take it once because the coefficient of x cubed is 1. Okay, we want 4x squared in f. We have to have 1 times the basis element x cubed plus x squared. We can use the basis element x squared plus x to make that 1x squared up to 4x squared. So we should take 3 times x squared plus x. At this stage, we've got x cubed plus 4x squared, which we want. We've got 3x. We'd actually like to have minus x. So we can fix that by adjusting using the third basis element x plus 1. So to get from the 3x that we have from the first two terms here to minus x, we should take minus 4 times x plus 1. And at this stage, we've got x cubed plus 4x squared minus x. And we've got minus 4, but we want minus 2 as constant term, so we should add 2 times 1. So this is saying that the coordinates of this polynomial fx with respect to this basis C3 of P3 are 1 as the coefficient of the first basis element, plus 3 as the coefficient of the second one, minus 4 as the coefficient of the third one, plus 2 as the coefficient of the fourth one, which is not obvious at all, like sort of glancing at the polynomial. Like there's a calculation to do here to figure out that representation. Okay, then if we want to use this matrix to calculate the derivative of f of x, what we should do is take the column vector with the C3 coordinates of fx, multiply it on the left by the matrix of the differential operator with respect to C3 and B2. When we do that, okay, here's our matrix. So the result of this multiplication, in the first entry, we've got 3 times 1 plus 0, 0, 0, so we get 3. In the second position, we've got 2 times 1 plus 2 times 3, so we get 2 plus 6, which is 8. In the third entry, we've got 0 times 1 plus 1 times 3 minus 1 times 4, so we've got minus 1. So this is saying that the derivative of the polynomial f of x should be the polynomial whose coordinates in B2 are 3, 8, minus 1, which would be 3x squared, plus 8x minus 1. And sure enough, by looking at fx itself and calculating its derivative in the conventional way, we can see that the derivative of fx is 3x squared plus 8x minus 1. Okay, so this matrix does indeed do the same job as the last one, but just with respect to a different choice of basis. So one of the kind of key considerations when you're representing linear transformations with respect to different bases, with respect to a basis, where there are two, one is to be aware that the matrix depends on the choice of basis. So, it's not exactly true that the correspondence between linear transformations and matrices is just sort of completely just that. It also depends on a choice of basis. And I guess the other remark is that, the matrix that represents the same linear transformation with respect to two different bases might not be as handy and nice to deal with as each other. And this is a case in point. I mean, the first version of the example had this 3x4 matrix, which is kind of almost resembling a diagonal matrix, although it's not square. It just has a sort of diagonal of non-zero entries starting in the top left, whereas the one that represented the same transformation with respect to this kind of less obvious choice of bases is not diagonal. It still has nice properties, like it still has a lower triangular matrix in its first 3 entries, for example, but it's not as nice probably as the original one. So it can be that there's a sort of some choices that are good or less good for describing certain linear transformations, and that's going to be part of our interest in this chapter. So on this particular example, I mean, the reason it's there is to point out that even in the case of linear transformations between spaces that aren't necessarily already written with respect to a standard basis, by choosing a basis, we can still represent the linear transformation with a matrix. Okay, so I'm not really suggesting that this is a recommended method for actually carrying out differentiation of polynomials. If anything, it's probably overcomplicating the issue, particularly the second version of it. But it is an example, I suppose, that we're familiar with, and so we can kind of verify for ourselves by trying it out with our example choices of polynomials that it does indeed work. And what it does do is indeed differentiate these polynomials, and it kind of uses a matrix multiplication mechanism to do so. So I'm not suggesting for a second that this is kind of how we should go about differentiating polynomials from now on. It's just to illustrate the point about representing linear transformations. So we're going to pick up this topic about different matrices representing linear transformations with respect to different bases, and we'll develop it a bit more and develop a kind of a systematic way of moving between the representations with respect to one basis or another, using the concept of the change of basis matrix that we saw this week in Lecture 13. Okay, that's it for this one. Thank you very much, everybody.